What's that? Oh, thank you. Anybody else? I think I might have missed Jimmy. Oh, you're okay. All right. I will begin with a word of prayer. Heavenly Father, we thank you for this day again. I thank you for this class and for your creation. Help us to glorify you what we do and just understand a little more about calculus this week, Lord. In my prayer, Lord Jesus. Amen. So, I sent you guys an announcement where I listed, a bunch of perhaps interesting examples that you can kind of resource and look at, and whatever you don't get from class, you can get more from there, I suppose. And as you can see, Professor Schmidt has left us an example, which I'll talk about eventually. But to start with, I want to talk about areas bounded by curves. So how do we calculate areas bounded by curves? So we can't just write down a formula and walk away from it. Like, we have to understand the geometry of the problem that we're dealing with in order to answer these questions properly, right? So like, example 1, find area bounded by, let's say, y equals x squared and y equals the square root of x. All right, so what I usually do with a problem like this is I start with a graph. All right, so let's see here. My y equals x squared, something like this, right? Y equals square root of x is something like that, up to the limits of my artistry here. Maybe I should have used a different color. Let me use a red for the square root. So what is obviously important here to understand the problem? Yeah? We need to understand what these points of intersection are, right? Because that's going to be critical to understand how to calculate the area here, all right? So how do we find those points of intersection? What is the nature of a point of intersection? It's where the defining equations of both curves hold, right? So if you can find something common to how both curves are defined, then you can set that common thing equal, right? In this case, it's kind of obvious. We have y for both, right? So we just set y equal to y. So to find points of intersection, we look at x squared equals to the square root of x, right? Yeah? And now how do you solve that? Whoa. I'm going to take a preemptive cough drop. Any ideas? How should we solve that? What's the natural enemy of the square root? The square, right? So square both sides. We get x squared squared, which is x to the 4th, equals to x, right? And how do you solve a polynomial equation? Well, my advice would be factoring. All right, so we can do, there's different ways to go about this. One way you could go about it is, well, let me just do that. X to the, good grief. Sorry guys, I'll get eventually. X to the 4th minus x is equal to 0. Factor out the x. I have x times x cubed minus 1 equals to 0, right? So how can that be solved? Either x is equal to 0, right? So you either have x equals to 0 or x cubed must be equal to 1, right? How many solutions does x cubed equal to 1 have? No, there's just one. We can take the cube root of the equation. Now the answer is really there's actually three solutions to this, but That comment is brought to you by another course, namely Math 331, Complex Analysis. See the three solutions to x cubed equals to 1? They're on the unit circle. There's the 1, there's this one, and there's also that one. Those are the three solutions to x cubed equals to 1. But these two are complex, so they don't count. But anyway, let me erase that from the record. I didn't say this in here. This never happened. Okay, so we've got two solutions, and obviously our points of intersection are what? 0, 0, and 1, 1. Now, when I've assigned this problem on tests before, I oftentimes have students figure out that the points of intersection here are 0 and 1 without even doing algebra, right? In a problem like this, I don't take up points if they do that, frankly, because I think it's actually somewhat obvious that the points of intersection here are at 0 and 1, okay? Now, at this point, the question is, how do we find the area? And the technique is this. What you want to do is you want to draw your typical approximating rectangle. So here, I'm going to use vertical rectangles like this. And the idea is I can slice this area up into a bunch of little, like rectangles like this. Chop, 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 right? And I can figure out what's the area of a typical one. Now I think infinitesimally. So what I mean is I think of the width of this as being dx, and I think of the height of this as being the top y minus the bottom y, right? So dA is equal to the top y minus the bottom y times dx. That's the area of this little slice, right? Now I say infinitesimal, but I mean, please understand, this is just a mnemonic, a useful way of describing finding a finite approximation. Like really you could chop it up into n boxes and take the width of each box to be delta x, and then take the limit of the number of boxes going to infinity. And then if you look at the limit as your approximating sum goes to infinity, you look at it, you tilt your head, you squint, and you go, oh, what do you know, a Riemann sum of a particular integral. But rather than telling you guys all that, I simply adopt the philosophy that we should talk about infinitesimal rectangles as a means of not talking about an explicit finite approximating sum and taking the limit. Because when I take a finite sum and I take the limit, I lose all you guys. And I don't think it really adds anything either to the calculational method. We can use infinitesimal rectangles and infinitesimal slices like over there to calculate areas, volumes, and more. This is what I broadly speak of as the infinitesimal method. But understand, it's just a shorthand for a complicated limiting process married to the Riemann integral. Okay, so for this problem, my dA, uh-oh, I feel it coming. What's the top y? What's the bottom y? Suppose you mixed up the top and the bottom. What happens when you calculate this at the end? What do you get? You get a negative number. Then you know you made the wrong choice, right? So you go back and you fix it. But this one, the top y, square root of x, and the bottom y is x squared. If you doubt me, try putting in a half. What happens? Like, what's the square root of a half? The square root of a half is like 0.7. What is 1/2 squared? It's 0.25, right? Which is bigger, 0.25 or 0.7? 0.7, right? So the square root is the bigger one, between 0 and 1. Now past 1, this story changes, right? The square root of x is below, x squared is above. So context matters, that's why the graph matters. When do I have such a slice? I have this for 0 less than or equal to x less than or equal to 1. That's what you have to answer before you can finish the calculation. You have to understand, where do you have an approximating rectangle, right? And the way to do this is to graph. Uh-oh. All right, so I'll try to hand you Let me set an alarm here so I hand you guys work back like a little bit before our class time's over. Uh-oh. Oof. Let's see here. Class ends what, 11:30? Like, ha ha ha, very funny. Let's see here. I just like that joke. Tell you what, oh, I'll try to hand stuff back to you guys at like 10:55. All right. Okay, so then how do we calculate the area? We integrate. So the area then is equal to area integral from 0 to 1 of the square root of x minus x squared dx. X to the 1/2 integrates to 2/3 x to the 3/2, right? Minus 1/3 x to the 3rd. These evaluate from 0 to 1. You got yourself 2/3 minus 1/3. So answer, the area is 1/3. All right, so when I assign these problems, I typically will have instructions that are something like, calculate the area bounded between the curves. Please include a picture of the region being, you're finding the area of, and also a diagram of a typical infinitesimal rectangle. Okay, so I do expect this picture. It is unacceptable for you to just write this down without explaining to me what you're doing. All right, you need to explain to me what you're doing. Example 2. What if we want to find area bounded by x is equal to, let's say here, y squared minus 4 and x plus y equals to 1. All right. How do we do this? So the first thing is, what is x equals y squared minus 4? Do you guys understand what that is? Maybe you haven't thought about this before, but if we switch the roles of x and y, what that means is the graph that you know has been turned sideways, right? So if I was to tell you y is equal to x squared minus 4, none of you would bat an eye. You'd just be like, well, that's a parabola. It opens up, it has a y-intercept of minus 4, right? So this, by the principle of exchanging x and y's meaning, this is a parabola on its side. That's right, parabola with x-intercept minus 4. That opens to the right. All right. And of course, this guy right here, you know what this is. What is this? This is y is equal to 1 minus x, right? That's a line, y-intercept 1, slope minus 1. So I can graph all this, yeah? See, I don't want to erase his stuff. Rats. What shall I do? If it's okay with you guys, I'm going to erase the blue from the last example. Is that okay? Yeah. I'm going to put the picture up there. So, here's the picture. So we've got a parabola that opens rightward, y-intercept minus 4. Right, there's my y, x equals to y squared minus 4, all right? And then I've got also y equals 1 minus x. Where does that look like? It's 1 minus x. It's something like, right? Now, so you see the area which is bounded, right? Is it clear? See what we're after? We're trying to calculate the area up in here, yeah? This area. Now think about this. What if I tried to use the approach that we used in example 1? Would that be a good idea? Why would it not be a good idea? What's the trouble there? Yeah.
It's not top and bottom, it's also left and right.
Yeah, it's not top and bottom, it's left and right. That's a good answer. Let me say more. Like, if I made it top and bottom, it would be super annoying. See, because I'd have to break it in 2 cases. Right here, from this point of intersection over, the top and the bottom are both given by the parabola. So I'd have to use the plus or minus solution to the parabola there. But then, when you get over here, the top is the line, the bottom's the parabola. So I'd have to break up into 2 cases, and it just would be unpleasant. So yeah, left and right is the way to go here. So what we do is imagine a typical approximating rectangle that looks more like this, a horizontal one, right? So now the thickness is not dx anymore, it's dy, right? And the width of this approximating region is equal to the right x minus the left x, all right? So that's what we're going to be up against here. Now what is the left? So you notice that the left x is actually this one, right? And the right x is given down here. If we solve for x, we've got x sub r is equal to 1 minus y, right? So you see what we have is we have a dA, I guess right down here, dA is equal to, you know, xr minus xl times dy, but specifically that is 1 minus y minus, use parentheses here, parentheses are your friend, y squared minus 4 dy. That is what we need to integrate. Okay? Over what domain? Where should we integrate this? What have I not done yet? So think about it, right? We can draw such a rectangle at each point here. From where? From this point all the way up to here. So we need to find these points of intersection in order to set up the integral. How do you find those points of intersection? So here, I think you absolutely have to show the algebra because I don't think it's obvious. Is it obvious? Can you guess it? I mean, I don't know. So look for something common. How about this? XL is equal to XR, right? So we've got y squared minus 4 is equal to 1 minus y. Well, that's not too bad. That's just a quadratic equation in y. We can solve that. So we've got y squared plus y minus 5 is equal to 0. Now, I just made this problem up. So like odds of it having integer solutions are somewhat slim. And if you complete the square here, you see we're get into fractions. I'm just going to write the answer down using the quadratic formula here because that's all I got room for. So you got y is equal to minus 1 plus or minus the square root of b squared, which here is 1. 4ac is plus 20, so it's 1 plus or minus 21 divided by 2, I believe. So b squared is 1, minus 4ac is 20, 1 plus 20 is 21, a is equal to 1, so I divide by 2. So it doesn't give me joy to write these numbers, so let me just call these y plus or minus, just for the sake of not writing that 10 times what we're about to do. So our area is equal to the integral from y minus to y plus of this character right here. What is that? 1 minus a minus 4 is 5. And then you've got minus y squared dy. So we just have to do that integral, and that will tell us the area between the parabola and the line. So we do the integral. We've got ourselves 5y minus 1/2 y squared minus 1/3 y cubed, evaluated from y minus to y plus, which is, oh, it's kind of ugly. So you have 5 times minus 1 plus the square root of 21 over 2, minus 1/2 minus 1 plus the square root of 21 over 2, quantity squared, and minus 1/3 minus 1 plus the square root of 21 over 2, quantity cubed, minus 5 times minus 1 minus the square root of 21 over 2, minus, well, rather plus 1/2 minus 1 minus the square root of 21 over 2, quantity squared, minus 1, well, plus rather, 1/3 minus 1 minus the square root of 21 over 2, quantity cubed. There you go. Man. Well, I made it that far. Anyway, any questions about this? I know that the integral is a bit of a mess. Like the actual computation of it is kind of annoying, right? So, whew. So I usually try to, when I put a problem like this on a test, I try to make it so excuse me, so that the points of intersection are like whole numbers, or at least fractions, you know, so it's not so horrible. But there it is. Whew. Now, if I was to put this in homework, if I was not an idiot, I would say, like, please leave your answer as a decimal, you know? So that at least we could compare easily. Any questions? Setting aside the annoying and somewhat complicated arithmetic of the answer, is the method clear? So the method is just this. We graph the region, and then we chop it up into pieces using appropriate infinitesimal rectangles. Excuse me. Example 3. All right. So we can do more areas, but I think it would be interesting today to actually show you everything. So I'm going to try to show you areas and volumes today, partly because Professor Schmidt has kindly left us this example. So why not use it, you know? So the next order of business is how do you calculate a volume? And so the one in front of us here, let me walk through it here. So we're supposed to take the region bounded by y equals x squared and y equals x. All right, and then rotate that around the y-axis, like that. You see that? If you can imagine that. And then we're supposed to find the volume of the resulting solid. So what he's done is he's used what's called the method of washers. Really? Crazy Paul. The method of washers says to take the volume and to slice it into a bunch of washers. So what he's doing here is he's like saying, so imagine the washer right here. Here's a picture of it blown up. The thickness of the washer, right, is dy because it's got a little delta y here. And it's got an R1 and R2. I usually call this the inner radius and the outer radius. The inner radius is fixed by the line inside, which is y equals x. The outer radius is fixed by the outside curve, which is y equals x squared. But if you want r, what is r x or y? See, r is the x coordinate, right? So the inner radius is x, the outer radius is also x, but you got the left x and the right x. This is the in the language I was just using in the previous example. I would say that the inner radius is equal to the left x, and the outer radius is equal to the right x. All right? And so he's like, his radius formulas, so his inside radius is y, his outside radius is the square root of y, right? So if you take this y equals x squared, you can solve that for x is equal to the square root of y. And then I just add an x sub r on it to emphasize that it's the right one, right? The other one is y equals x. How do you solve that for x? X equals y. Yeah, it's nothing really happened there. So now what's the volume of the washer? The volume of the washer is the area of the annulus. An annulus is just the area between two circles, right? So the area of this annulus times the thickness gives you the volume, which is to say that the area times dy. So he says the change in volume is the volume of the outside disk minus the volume of the deleted disk, which is, in this context, giving us pi times y minus y squared delta y. And then, I'm sure he has about a paragraph of jibber-jabber about Riemann sums and stuff here. And then in the limit that delta y goes to 0, right? And the number of washers goes to infinity, you get the Riemann sum as below, right? And so we integrate that and so get that the volume of this, what's called solid of revolution, is pi over 6. So when I do this, I usually write something like, I would say something like this: dv is equal to pi times r out squared minus r in squared times dy, right? Which in this context is pi times y minus y squared dy. And then you just have to integrate that. Why did he integrate from 0 to 1? We have one of these washers, right? You can imagine a washer here, like all the way up until right here, right? So the dy will always indicate the range of the integration is based on y. If you've got a dy, you need to figure out what the maximum minimum extent of your y variable is for the region you're finding the area or the volume. So here, y equals to 0 is right here, right? And up here is y equals to 1. How would you find those? You need to solve the intersection, right? You set the different curves equal for both for y, right? Like, for instance, you'd have, where is x squared equals to x for this one? So that's x squared minus x equals to 0, which gives us x times x minus 1 equals to 0, which either gives us x equals to 0 or x equals to 1. But then what? We're talking about the curve y equals x, right? So that translates then into either y equals to 0 or y equals to 1 for my points of intersection, yeah? Or if you like, use the other equation. 0 squared or 1 squared for y. We're still going 0 to 1. All right, now that we've done that, let me erase, and we'll go on here. Oh, I guess well, here, let me ask you guys a slightly different question. Example, I guess this was our example 3, right? Example 4. So I'm going to turn the tables on you guys. I want to ask you, can you calculate the integral from minus 1 to 1 of the square root of 1 minus x squared dx, all right? I'm gonna let you guys work on that for a minute. I'm gonna go get a cup of coffee, and I'll be right back. My apologies for leaving you guys, but I'm about to start coughing very violently again. I need some coffee. But see if you can calculate this. By the way, don't try to find it. Well, do find it, try to find an antiderivative. More power to you. See if you can do it. But if that doesn't work, try to understand this geometrically. What are we finding the area of? Think about that. I'll be right back. Anybody find an antiderivative? Nobody? Yeah?
I think. Are you ready?
I'm listening.
So I got 2/3 x times parentheses 1 minus x squared to the 3/2. Plus e.
So you said 2/3. What was it?
Wait, 2/3 x. 2/3 being
X.
parentheses,
Mm-hmm.
and then 1 minus x squared, and then parentheses, then set that to the 3/2,
Uh-huh.
and then plus e.
Oh, plus C, okay. Let's try to differentiate this. All right, so like product rule, right? So I got like 2/3 times 1 minus x squared to the 3/2, and then plus 2/3 times 3/2, 1 minus x squared to the 1/2 times 2x. This is almost what you want. Like this piece is almost what you want, but yeah, no. Sorry, no. The derivative is not back where we started.
And so that one, you don't multiply the 3/2 times the 2/3 x, take it just x, and then you multiply by the inside, the derivative of the inside, which is negative 2x.
Whoa, wait, what?
Never mind, I'll take something else.
Okay.
Channel.
Yeah, I mean, well, here, full disclosure, here's why you guys can't find it. Integral, and don't tell anybody I told you this, you're not supposed to know this yet, but if you want to solve this integral, what you do is you let x equals to like, oh, I don't know, sine theta. Then dx is cosine theta d theta, which makes this the integral of the square root of 1 minus sine squared theta. And then dx is, well, cosine theta d theta. Lo and behold, we've got the integral of cosine squared theta d theta, which is the integral of 1/2 1 minus sine 2 theta d theta, which integrates to theta over 2 minus 1/4 the cosine of 2 theta. But I need a plus there because it's cosine. Oh, my bad. What's cosine? That's a half angle formula. I'm a dummy. Cosine of 2 theta. That integrates to, so yeah, it was a minus sine 2 theta. Plus a constant. So, yeah, if I'm going to integrate, and then, so yeah, I mean, why didn't you guys just guess the antiderivative? It's only like, you know, what is theta here, by the way? Well, here, let me change, let me just forget, let me just go ahead and do the integral. So here we have integral from -1 to 1 of the square root of 1 minus x squared dx is equal to theta over 2 minus 1/4 sine 2 theta, evaluated from what to what? Well, you see, what's this say? X equals to 1, theta equals to what? X equals to -1, what should theta be? How do the bounds translate with this substitution? How can I get how can I get sine of theta equal to 1? I need a theta equal to pi over 2. How can I get -1? 3 pi over 2 is not wrong, but we'd like the integration domain for theta to be one continuous swipe. So we want the closest one to pi over 2, which is actually back behind the, yeah, negative. It's minus pi over 2. But 3 pi over 2 was a totally legitimate response to that question. So minus pi over 2, in fact, that's really good, pi over 2. What happens when you plug pi, plus or minus pi over 2 in sine 2 theta? You get what? What's sine of pi? What's sine of minus pi? These are 0. And so what we get is simply pi over 4 minus a minus pi over 4. What's that known as? What's a quarter plus a quarter? Pi over 2. The answer is pi over 2. Listen, I am not trying to say you guys need to learn how to do this. This, my friends, is what's called trigonometric substitution. This is a calculus 2 technique. Now, you might think, this is what we did though, isn't it? There is a subtle but important difference in the substitution here. Think about the difference. So like we do substitutions like this. E to the x squared, you know, maybe times 2x dx. We'll go, oh, okay, well that's the integral of e to the u du. Right? Our substitution variable is u. U is equal to x squared. See the difference in what's being done? With this substitution I just made. Yeah? See this right here? What's the substitution variable? What's playing the role of u? Theta. Theta plays the role of u. Theta is the substitution variable. So this is what you might call an implicit substitution. Whereas this is an explicit substitution. Explicit means that you're writing the new thing equals to stuff, whereas implicit means that the new thing is being defined by some kind of intertwangling relation. It's not direct, you know, it's implicit. Anyway, this is a calculus 2 technique. I don't expect you to learn it here. You're like, well, then why would you ask me this question? And then I would ask you the question, why does my brother put this on calculus 1 tests like every semester? He asks students to find the area of this curve. Why is that a reasonable question? What is this curve? What's that? A circle. Right. And see, this is y is equal to the square root of 1 minus x squared, right? That's the integrand. So if we square that, we get y squared is 1 minus x squared, also known as x squared plus y squared equals to 1, right? So this is equal to the area inside circle. Unit circle above x-axis, If you draw a picture of it, this is the curve we're finding the area under. Y is equal to the square root of 1 minus x squared. So this is a kind of nasty trick problem for you guys. It's less nasty now that I told you about it, but still nasty. So the area, of course, is half the area of the unit circle, but you guys know that the area of the unit circle is pi, right? Because we know the area of circle is pi r squared. You might be like, well, you haven't derived that yet. I would remind you I derived it on CFAW day. I took the limit of the number of triangles inside of circles inscribed goes to infinity, and we saw that the area of the circle was pi r squared. I gave you a limiting argument from chopping the circle up into an infinite bunch of triangles. You don't remember that? Oh, you remember that? Okay, that's good. But also, it's just default knowledge. Like, I don't deny students formulas from middle school about geometry, right? Like, I'm not going to be like, well, you can't see the area of a triangle is 1/2 base times height because we didn't do that here. No, like, you're allowed to use that. Length times width for the area of a rectangle, that's allowed. If you knew the volume of a cone, go for it. Hey, let's calculate the volume of a cone. What do you say? All right. Sorry, now that I've got past the silliness. But the silliness here is that you can't do the integral, right? What's not silly is asking the question, what geometrically does a given integral mean? That's actually a very good question. So let's go on here. So student's choice, area or volume? Volume? All right, volume it is. Let us calculate the volume of a right circular cone. So there's different kinds of volume problems. There's volume problems which are based on like finding the volume of a, like a solid of revolution. There's other ones that are based on like calculating the volume of a shape which has just like a regular pattern, so you can slice it. And if you can take the volume, if you can take the shape and slice it into a regular pattern, then you can calculate the total volume by integrating the volume of the typical slice. So like a cone is a good example of this. So I guess that was example 5. So a right circular cone, it's got a circular base, right? And then whee, like this, right? And so the two things of interest are the radius r and also the what? The height, yeah. So this I'll call height h. And what makes it a right circular cone is that the sides the slope of the cone is linear, all right? You could imagine other cones which have like a curved side, right? Like a curved cone, you could imagine things like that. But that's not what we're imagining at the moment. So my point is that the sides are straight. If I was to, lie my markers, you could form this. You could form this indeed as a curve of revolution, right? You could take the line like this and then just rotate it around like that. You could make the cone by rotating. Wait a minute. Yeah, rotating. I can't ever do that. But so how are we going to calculate the volume of such this thing? So what I do is I chop it into washers. Actually, discs in this case. So here, I just think about this disc right here. And we use Y sometimes, but this time I'm going to use Z just to be different. So I'm going to say the thickness here is dz. And this is at distance Z from the base. So basically, the bottom of the cone for me is Z equals to 0. The tippy top of the cone is Z equals to H. All right? And let me call the radius of the washer S. All right, the radius of the washer is S. Let me make a bigger picture. So I'm just drawing half of the cone in some sense, right? But here's that S that I was just drawing, right? So down here, there's R, right? So in this big triangle, what's this total distance? H, right? The total distance is H. What is the distance here? Oh, H minus, very good. Thank you. Good point. I should add that to this. This is Z. So this right here would be H minus Z. Cool, yeah. So how can we relate H and Z and S and R, right? H and R are given. Any ideas? What do you guys learn about in geometry? Or Algebra 2 or Algebra 1. I don't know where you guys learn things. Maybe your grandma taught you. What? Grandmas don't teach you about math? Could happen. My grandma taught me about geometry. She told me she took geometry 3 times. First time she got a 30%. The second time she got a 60%. And the third time she got a 90%. Let us not follow her example in calculus, yes? So, must have been a struggle. All right, so we can use similar triangles, right? So similar triangles says the ratio of similar sides is equal. So similar triangles tells me that S over H minus Z is equal to what? So S is to like the little red, let me make it green, the green triangle, right, this guy, is similar to the giant black triangle, right? So S divided by H minus Z should be equal to R divided by what? Nobody? H. Very good. So we can solve this, and we've got our formula. S is equal to R divided by H times H minus Z. There you go. This describes the radius of the slice as function of Z, the height of the slice. Right? Notice that H and R are given. And let's check our formula. Check the formula. Does it make sense? What happens when Z equals to 0? What do we get? R times H over H, which is R. Right? That's good. What happens when we put Z equals to H? H minus H is 0. The slice has 0 radius at the tippy top, right? So this is one way you could find the... Now, when I was a student, yeah? Yeah, we can do more. But yeah, this could be something that's on the test. Now, there is another way to derive this as opposed to similar triangles, which is to go, well, the side has a linear shape to it, right? So I can kind of like know ahead of time, if it's linear, that means S should be a linear function of Z. So I can guess that S is equal to mz plus b. And then I can find B, M and B to make it so, right? Like S of 0 has to be equal to R, right? So that's M times 0 plus B. S of of h has to be equal to 0. So that's mh plus b. All right? So we've got two equations, two unknowns. We can solve for b and for m. See, the top equation immediately tells us that b is equal to r. All right? Remember, r and h are given. So we're trying to solve for the unknown parameters of my radius function using these givens, r and h. This says that m is equal to minus b over h, which is minus r over h. Put these together, what do we got? We have s is equal to minus r over h times z plus b, which is plus r. So you guys compare this equation and this equation. I refer you to the Office meme with Jen. Jen? What's her name? The main female protagonist for The Office. Man, I've forgotten everything. Oh well. These are the same formula, right? This is the same thing. So this way, this way is a nice way, like we just assume that it's a linear function and we find the slope and the y-intercept for the formula basically using the data, which is obvious, namely that the radius is r when z equals to 0, the radius is 0 when z equals to h. That's one approach. I like this approach more when I first did this stuff because similar triangles never are apparent to me. But for others of you, similar triangles are like a happy place for you, and so me making an argument by similar triangles gives you peace. Maybe there's no one in here. Maybe I'm wasting my time with a similar triangles argument. I find this to be, the algebra I just did, I find to be more reliable and sort of scalable to other examples. So I encourage this method. We're not done, right? All we've done at this point is what? We have found the typical radius as a function of z. Why does that matter? Well, what's the volume of the slice? Can I erase that? Oh, no. Fun. I'm going to erase this. I'm going to leave us one of the formulas, though, because we're going to need it. So dv is what? The volume of the slice is pi s squared times dz. Why is that? The area of the slice is pi s squared, right? The thickness is dz. So that's the volume. And then, so the total volume, I integrate integrate from 0 to h of pi. My s was, I'm going to factor an r out of that if that's okay with you guys. So I got pi times r squared times 1 minus z over h quantity squared dz. Let's do the integral. Square that out, what you got? We've got 1 minus 2z over h plus z squared over h squared dz. All right. Integrate. Pi r squared is a constant. I'll pull it out front. And then we've got z minus 2z squared over 2h, and then plus 1/3 z cubed over h squared. I got to take all of this and evaluate from 0 to h. What do I get? 0 gives me nothing, right? Nothing. And then if I plug in h, I get h minus h squared over h, right? plus 1/3 of h cubed over h squared. I'll write it out. So these two guys cancel, right? The first two terms cancel, and we're just left with 1/3 pi r squared h. The well-known, well, perhaps well-known, I'm not sure how well-known it is, but that is the formula for the volume of a right circular cone of base radius r and height h. We can derive it with calculus. Does that make sense, guys? Yes, no, maybe so? Si, senor, I will allow it. I ate La Coretta this week even, so, you know. Oh, is La Coretta good? Is the sky blue? Do you breathe air? Is water wet? These are similar questions. Is La Coretta good? I mean, actually, it depends on the day and the quality of lettuce in the region, but. As a general rule of thumb, I have had very few bad experiences at La Coretta. In any of the locations. Timberlake one's good. One on Wards Road is good. There's one in Rustburg I tend to go to. Also good. So, let's see here. Should we do another one of these? What do you guys want, area or volume? Let's do another area. We haven't done enough area yet. Let me do an area one which forces us to break into cases a little bit. So, find the area bounded by, let's see here. But Mia, we'll do more of these, hopefully like tomorrow. All right, so I'll give you guys more examples of these slicing examples. So let me draw a picture of us. Sometimes they're kind and we get a picture to start with. So we could have something like this, for example. Y equals the absolute value of x, right? And we could say, then we could have something like, oh, goodness gracious. Y-intercept here, maybe 2 over there. that was supposed to be a parabola. Oh well. My drawings are, it's like the nuclear bombs have fallen and all my graphs are starting to melt or something. But so that's kind of violent. Let's see here. Anyway, so there's y equals the absolute value of x is the black one here, and I want a parabola which has x-intercepts of like -1 and 2. So we're looking for y equals to, say, x plus 1 times x minus 2, all right? So find the area bounded between these curves. Can we find the area bounded between these curves? Yeah? So if you look at this problem, like the left-right thing doesn't make it nice, yeah? The up-down, I mean, it's just not nice. We have to break up into cases for this one. I think vertical is the way to go because essentially you can look, you've got 2 cases, right? It's either like here or like here. Well, I guess it's always the same. It's always absolute value on the top, right? So I guess I could always say that dA is equal to, absolute value of x minus whatever this works out to, x squared